Roger, you're loud and clear here also.
Space Nuts.
Thanks for joining us. And don't forget the Space Nuts shop is on our website, where you can go to, peruse our stock, whether you want a pair of flip-flops or a cap or a hat or a mug or a sticker or a bomber jacket. There's a vast array of material there at the Space Nuts shop, where you can, buy something for yourself or a friend or a hard-to-buy-for uncle. It's spacenutspodcast.com, and just click on the shop button, spacenutspodcast.com, and then click on the shop button to have a look through the Space Nuts shop. Now, I have something very, very important to say. Young Ashley, who sent us those squillions of questions last week, suggested we needed a sticker that says, "I am a space nut." Ashley, I am very, very pleased to report that Hugh thought that was the greatest idea in the world, and he's going to do it. So we will be getting an "I am a space nut" sticker. And Fred, we got a lovely note from Ashley's mum saying thanks for answering all his questions. It seems like we've sparked a lot of enthusiasm in young Ashley, and we're very pleased to have been able to get all those questions answered for him. And we're going to answer some more now. We've got a whole bunch of text questions, and we don't do enough of these, so we'll focus on these today. Now, this first one comes from Richard on the Sunshine Coast, and he says, our current technology lets us peer back to a galaxy 14.2 billion light years away in the infinite universe. If we went to where that galaxy is seen, to the point where it was all those years ago, and peered out again with our telescopes, I assume we would find another galaxy somewhere that is also 14.2 billion light years away. And if we went to where that galaxy is presently located, would we be able to see the same, another galaxy 14.2 billion light years away, and so on? Or is it the case that no matter where we are in the universe, we would always find something 14.2 billion light years away? Or the opposite, is there any place in the universe where we could only find objects less than 14.2 billion light years away? How does this not infer an infinite universe? Could space curve back on itself so that we still have a finite and expanding universe and still be able to peer out 14.2 billion light years no matter where we are? It's all too hard for my head to get around. Many thanks for your outstanding show. Cheers, Richard. He's been really pondering this one, from what I can tell.
Yeah, it's a great question, and it goes to the heart of how we think the universe behaves. It might be an old report that Richard was looking at, because by today's measurement standards, the furthest galaxies that we can see are around about 13 billion light years away. Although that's not we glibly talk about them being 13 billion light years away, but in fact what we really mean is that we've got a look back time of 13 billion years to them, because their true distance is probably much more than that, because the expansion of the universe is probably more like 30 billion light years. So anyway, that's a detail that doesn't really matter in this discussion, because he's absolutely right that if we could be where that galaxy was, let's say it's 13 billion light years away from ours, and had a look, we'd see the same thing as we see now. We'd see galaxies all around the sky. We would see the most distant ones would be about 13 billion light years away that we could see. And then if you went to another one, it would be the same picture. Now, if you can do that ad infinitum, it suggests an infinite universe. Actually, it doesn't suggest that. What it suggests is an unbounded universe, one that doesn't have an edge. Because you can have a finite universe that is unbounded. If you think of the surface of the Earth, the surface of the Earth is definitely finite, but it doesn't have boundaries, because you can keep going, forever. And that's the point of Richard's last comment, that is space curved back on itself, so that it looks as though so basically you could go all the way around and come back to where you started from. The current thinking eventually, yes, after a week or two. the current thinking is that it's probably not, that we've got what's called a flat universe. So the geometry of the universe means that it is kind of like the geometry that we've got around us. It just goes on forever. And that, so yes, the answer is we don't know. There are many cosmologists who believe that the universe probably is infinite, or at least unbounded, just to come back to that idea, but maybe infinite, because if it's a flat universe, it's not curving back on itself. So it's really at the forefront of physics, and Richard's struggling to get his head around it is about the way I do as well. It's one of the point is that we only know what we can see from our vantage point, and what we find is what we call an isotropic universe, one that's the same in all directions. It could be that as you move through that universe, maybe that would change. Maybe you would find places where the density of matter was different, and that would cause the universe to have a different curvature, because it's the matter in the universe that gives it its curvature. When you're thinking about, space bending back on itself. So from our perspective, it looks as though it's infinite, but we can't answer for the rest of the universe. We can only talk about our bit.
So Richard, Fred just took 25 minutes to tell you we don't know.
No, to tell him he's right.
He's right.
He's right.
Okay, that's
we
a fair
don't know.
enough assumption. Yes. No, but it is, I suppose, one of the biggest mysteries of the whole existence of existence, because these are the questions we're pondering and the questions we're trying to answer. And, we're chipping, as I've said before, we're chipping away at these things. And every time we chip something away and go, aha, we answer a question, and then we've got 3 more to figure out.
Yeah, that's right. The chips get bigger. It's a bit like the Sorcerer's Apprentice, as you yes. chop up one question, 20 more appear.
Yeah, it is like that, very much so. Anyway, Richard, there you are. That's the latest that we have on the ever-expanding universe. And thank you for your question. Now, we'll move on to the UK with Mark in Newbury. This is a short and sweet question. We know the hydrogen fuel in our sun will run out in approximately 5 billion years. What controls the rate of fusion between hydrogen atoms to prevent the fuel from being burned up much faster, to the point of happening instantly, or slower than the current rate? The price of fuel out of the Middle East, I think, would have something to do with it, but I suspect I'm wrong.
No, you're on the right track. So the fusion process is essentially that basically hydrogen nuclei, which are protons, in fact, I think it takes 4 hydrogen nuclei to fuse into one helium nucleus, and this is the process that drives the energy of the sun. And it's the figures I'm looking at here, about 0.7% of that fused mass is released as energy. So it's a process that it's discrete in the sense that it needs a certain number of hydrogen nuclei to make the helium nucleus and release the energy. And that process has got its own clock. In other words, it always takes the same length of time. So that, I think, explains part of the question. It's Mark's question, isn't it? So the rate of that fusion is not a random thing. It depends on exactly which atoms are coming together and how the energy is released. It's a gamma ray photon that's released. That is something that takes a specific time, and that's what causes the thing to sort of have this built-in clock with it. And then you've got to lump, as well as that, you have to lump the amount of hydrogen that's in the sun. So the bigger actually it's not intuitive either, because the more hydrogen you've got, the faster it burns. It's a bit the wrong way around. You'd think the more hydrogen you've got, the longer you would have. But it's the massive stars that burn through their hydrogen most quickly. The current rate of hydrogen burning is about 600 million tons per second. It goes through. And of that, about 4.2 or 4.3 million tons is turned into energy. And it's that direct fusion of that, that amount into energy that gives us the heat and light of the sun. That's going directly from mass into energy, being multiplied by c squared, by E equals mc squared. So that's why you get so much energy from what is not that big an amount, 4.3 million tons per second. I mean, it is a lot, but it's when you think of the solar system bathing in the heat or basking in the heat and light of the sun, that 4.3 million tons per second gives a hell of a lot of energy.
Oh, yeah, absolutely. You can see it happening up in Canada at the moment with some of the record temperatures they've had. That is just extraordinary.
It is amazing. Yes, that's right.
What the record temperatures, as in, multiple degrees above their previous records. We're not, there's some places that have had temperatures 12 degrees above their previous records. I mean, they're just massive numbers.
Incredible.
And I think I saw a story this week about, now where was it? I can't remember. But one of the, I think it was one of the Greek islands or something, it had the biggest fire in history this week. So there's a lot of energy beaming down on us, and it's quite destructive at times, unfortunately. So yes, it is. There is a reason. It's and it's an interesting point that the bigger the star, the faster it burns.
Yeah, that's exactly not what you expect. I need to look into that one.
Well, it seems logical to me, because it's the same with cars.
Yes, I guess that's
the bigger they are, the more they burn. Yeah. Anyway, hope that answered your question, Mark. Thanks for sending it in to us. I know you've probably been waiting for that one to be answered. You've probably given up waiting for that one to be answered, but we got to it. Anyway, coming up, we're going to infinity and beyond with our next question here on the Space Nuts podcast with Andrew Dunkley and Fred Watson.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Space Nuts.
You've been listening to the Space Nuts podcast.
Available at Apple Podcasts,